Now let us start with Bernoulli's, let us start with Euler's equation. On the last lecture, we talked about Euler's equation and we said that Euler's equation is del v by del t plus v dot del v, which gives us an idea about total acceleration, and that is equal to component an acceleration which is caused by pressure and acceleration due to gravity. We will talk about it, but before that let's talk about concept of motion pressure. Concept of motion pressure in incompressible fluids. We are talking about incompressible flows, and in incompressible flows we are actually talking about that what causes this fluid flow. This fluid flow is caused by two kind of forces, body force and a pressure and a surface force. Body force is acceleration due to gravity, and surface force is the pressure force. If it was a compressible flow, then pressure would have also been utilized in changing the density, but in incompressible flow, the pressure and the acceleration due to gravity, this body force, they both are actually contributing to accelerating this flow. They are the reason because of which the flow happens. So let me write Bernoulli's equation here, and maybe this would become let me write Euler's equation and things would become a bit more clear then. So del v by del t plus v dot del v, this is equal to minus 1 by rho naught. It is the density of the fluid, P plus G. So that's what we have. On this side we have effect, which is acceleration, and on the right hand side we have cause, okay, due to pressure and gravity. The concept of motion pressure is nothing but what we are trying to do is to find is to eliminate this effect of gravity and include that into pressure. What we are trying to find here is what is that pressure because of which we are going to get this acceleration, okay, the total amount of pressure. To find that, what we are doing is, let's say how much what would be the overall pressure if the velocity v is 0, okay, if the velocity v is 0, how much would be that stagnation pressure, which if released would give us finally v velocity. So that bottled up pressure, how much would that be? And if we release that pressure, then how much finally velocity we would get? So initially the pressure available to us for fluid acceleration, that would be found if we put our velocity to be 0. Then from above equation we would get that 1 by rho naught del ps. So s is here for stagnation, plus g would be 0, and this would give that this g is nothing but 1 by rho naught del ps. If I put this value of g back in my Euler's equation, then I would get del v by del t plus v dot del v. This would be equal to minus 1 by rho naught del p minus ps. So let me call Pm is the total pressure which causes motion. So this is motion pressure. This is equal to P minus Ps. So what is Pm? Pm is motion pressure, or I can say that this is the pressure available for fluid acceleration. So that's what this is. Okay. So now this equation can be further modified and written as del V by del T plus V dot del V. This is my total acceleration. This is equal to 1 by rho naught del Pm. So left hand side is the cause, right hand side is the cause, and left hand side is the effect. Here, if you would see, what we have done is that we have eliminated the gravity force and taken its effect into Pm. Where does it help us? Instead of two variables, we are writing everything into one variable. Then many a times computationally it helps us a lot. Now, after this, let us move on to the next subtopic within Euler's equation, and that is Euler's equation in streamline coordinates. Up till now, we were following a particle along its path. Okay. Now, what would happen if that path is a streamline? So that's what we are going to do now. So Euler's equation in streamline coordinates, and we are taking that streamline in 2D. So we are talking about 2D here. Okay, no 3D. So let us say that this green is my streamline, and let me say that I am at point P here. Okay, at point P, along the streamline, my unit vector is ES. Perpendicular to this streamline, my unit vector is EN, and this is point P. This point P is, this streamline actually has a radius R. The streamline has a radius R, and if I am following this streamline, then the coordinate would be S. So let's say if it was an X, Y, Z coordinate system, then if I am moving along X-axis, my X value would change. If I am moving along Y-axis, my Y value would change. Here I am moving along a streamline, then this small s would change. Okay. From the horizontal, okay, this ES currently is making an angle of theta. This green line is my streamline. So the path the particle is taking is a streamline now. That's the only change which I have done. So velocity v of this particle, fluid particle, would be the magnitude times Es. I know about my acceleration. Acceleration would be del by del t plus v dot del v. This is my acceleration, I know about it. Now, what is del here? I need to find my gradient for this particular case. So let us see. Del here would be Es del by del s plus En del by del n. That is my del. If that's the case, then my acceleration A of the particle would be del V by del T plus V del by del S of V, and this could be written as del by del T. What is my velocity? Actually it is VES plus V times del VES by del S. If I rearrange and do differentiation by parts, I would get del V by del T plus V del V by del S ES, that is the ES component, and V times del by del T ES plus V del by del S ES. Okay, that's what this is. Now I need to find values of different parts. So what is del ES by del T? This can be written as del by del theta of ES multiplied by del theta by del T, differentiation by parts. Now del ES by del theta, if you would go to your mechanics book, the first year mechanics book, then you would see there that del ES by del theta is given as En. Okay, it's given as En. And where does it come from? So let's say I have here ES, okay, and it moved a little bit. And then I have ES dash here, and the angle made here is del theta. Okay, so if this is unit vector ES, since it's unit vector, so this length would be equal to this length. For the limit del theta tending to 0, we would find that this vector here is perpendicular to ES, and this is what is known as En. You would find that. Okay, and for more detailed derivation, you can go to your statics book and you would find a more detailed derivation over there. So anyways, moving forward, del ES by del S, this is del ES by del theta and del theta by del S. Now this del S is minus R del theta. Okay, again, how do I know that? So let's say this is my radius R, this is making an angle of del theta, and this is my arc length del S. So you know about it, how to find that out. That's what I have done. Now why the negative sign? I have taken by convention such a way that del theta is negative and del S is positive along the streamline which I have drawn above, the green figure which I have drawn above. So this is my convention. Okay, if that's the case, then I would get del ES by del S equals to minus En by R, where R is the radius of curvature. If I now substitute all of these values back in my acceleration, small a, I would get del V by del T plus V del V by del S. This is the ES component of acceleration, and V del theta by del T minus V square by R En. This is the En component of acceleration. Okay, so now my Euler's equation would look something like this: del V by del T plus V del V by del S ES streamline component plus V del theta by del T minus V square by R. This is perpendicular to streamline. This is equal to minus 1 by rho naught del Pm. Pm is my motion pressure. So now this is my vector equation. Okay. Now this would give me two components. If I want to find that how the variation happens of my pressure along a streamline, then I need to take streamline component, and I can say that along the streamline del V by del T plus V del V by del S would be equal to minus 1 by rho naught del Pm by del S. It gives us variation of Pm, which is my motion pressure along streamline, and the second component would be perpendicular to streamline del V del theta by del T minus V square by R equals to minus 1 by rho naught del Pm by del N. Gives variation of Pm normal to streamline. Okay, so we have now variation of pressure along the streamline and perpendicular to the streamline, and you would now find out this is the Euler's equation based on which we have this experiment of rectangular bend. All those readings of pressure which were taken on rectangular bend, they are based on this one. So the rectangular bend experiment is something like this, that you have a rectangular band, and you know, there is air being blown. This is the fan, air is being blown here, and you have pressure tappings along the radial direction, and then you have pressure tappings along the streamline direction. And what you do is that these pressure tappings are attached to a manometer, and you take pressure readings. So the variation which you are getting along the circumference, that is based on this streamline equation. And the variation which you would get along the radial direction is based on the component of Euler's equation normal to the streamline. So that complete experiment is based on Euler's equation. Now let us see what further conclusions we can make. Certain remarks. Now for a straight streamline, not a curved streamline. So for straight streamlines, the radius would tend to infinity. If that is the case, then this V square by R, this term would go to 0, and we can say that V del theta by del T would be equal to minus 1 by rho naught del Pm by del N. Further, if flow is steady, then del theta by del T would also be 0, and what we would get would be del Pm by del N is 0, meaning by that for straight streamlines, straight streamlines, parallel straight streamlines, where the flow is steady, there would be no pressure variation normal to streamlines. Let me show it with an example. This will become a bit more clear. Let me show it with an example what I'm trying to say here. Okay, let's say I have a pipe here, and within this pipe, let's say I have an orifice. Okay, and flow is happening here. At the start, my streamlines would be parallel. Okay, something like that. And then I'm drawing a particular case of a streamline. It would curve in here, and after a little while it would become parallel, and then it would move on something like this. Another streamline, one of the streamline, it would be something like that. In this way, after a while it would be parallel, and then again try to fill this whole space. One streamline, another streamline. So I am saying here at this particular location, okay, I would say that del Pm by del N is equal to 0. Again here, when they become parallel, again del Pm by del N is 0. Since the streamlines are parallel, so pressure would be uniform, and that is another concept which is used in wind tunnel, designing wind tunnel. The test section, where should our test section be and how the test section is designed, it is designed in such a way that within the test section you would get uniform flow and there would be no pressure variation in the wind tunnel test section along perpendicular to the streamline. So that is one observation which we can make. Now let's talk about next observation. How about if we have curved streamlines but steady flow? So curved streamlines with steady flow. Again, the equation is V del theta by del t minus V square by R equals to minus 1 by rho naught del Pm by del N. This term del theta by del t would go to 0, and what we would have finally would be V square by R equals to 1 by rho naught del Pm by del N. Okay, this implies that del Pm by del N would be equal to rho naught V square by R. Okay, that's what we would get. And the next thing which we can get from here is that del Pm by del N is positive, because rho is positive, velocity is positive, R is positive. Now this gives us an idea that Pm is higher on convex side than on the concave side. Of a curved streamline. Let me show that by drawing in a streamline. What do I mean here? So let's say I have drawn a curved streamline here. What I am trying to say that convex side would be more than the concave side. If I would like to see the pressure above and below that streamline, so it would be increasing more towards the convex side as compared to the concave side. this is my R moving on. And that is the reason that in your bend you would be seeing that along the radial direction in the rectangular bend experiment you would see an increase in pressure. And that was another reason that you would have seen rectangular bend also. You would have seen in the bend losses case also that I talked about, that secondary flows also develop. So let me show you what I was trying to say. So let's say this is a bend. Let's say this is an easy bend instead of a sharp bend. This is an easy bend. So what this shows that if I'm taking a cross section here, okay, and this cross section is A dash and A, so I would have pressure increasing in that direction. So pressure would be increasing in that direction, okay. So at the A dash side there will be more pressure as compared to A, provided I have drawn it in such a way that G is down here, and let's say if it was a circular pipe, and for the circular pipe, let's say this is my circular pipe, and let me give you a little bit of idea of what's happening here. And this cross section is this A dash. What I would see here is a secondary flow happening, secondary flow patterns. Secondary flow. Why? Since there is more pressure towards the convex side than the concave side, because of this pressure difference there would be flow happening in this way. Also there is flow happening in this direction along G, and then there is this circular flow pattern, and that takes energy from the fluid, and because of which there are losses, okay. And this is something which you have done in your experiment. If I would show you through another demonstration, let's say I have my streamlines which are like this, okay, and then like this. So if I'm moving along CD or along AB, so if I'm going from C towards D, this is I'm going towards more convex side, so PM is increasing. And if I'm moving from A towards B, which is concave side, so it's my PM is reducing, it's decreasing. So that's pretty much it about Euler's equation. So earlier we discussed Euler's equation in general, and then Euler equation along the streamline coordinates, so across the streamline and perpendicular to the streamline. Now let us move from here to Bernoulli's equation. You can talk about Bernoulli's equation in terms of energy of work. So it's a work energy principle which we are using, and that's why from momentum equation, general momentum equation, we move to a specific case of inviscid fluid, and that was Euler's equation. And from Euler's equation we can move towards Bernoulli's equation. So let's do that. Let's move to Bernoulli's equation. Okay. Let us see what we are going to do here. The Euler equation, which is actually a vector equation for inviscid flow, okay, so it's Euler equation which is a vector equation for inviscid flows. Okay, Euler's equation. Now it can be transformed into a scalar equation, and let us see how to do that. We can transform it into a scalar equation, and for that what we would do is that we would take again particle moving along a path, and that path is, let's say, it's moving from 1 towards 2, and this line is actually nothing but a material line. So we are looking at a particle which is moving in such a way. At particular instant, this particle is here, its velocity is v tangent to this line, and let's say along this material line it has moved a distance of dl. Why? Because of forces which are acting on it, and the acceleration would be a, and this a acceleration is caused due to the forces acting on it divided by the mass of the particle. So that's what we have. Now this equation is nothing but F equal to ma, and for an inviscid flow you would see that this is our Euler's equation. This is del V by del T plus V dot del, this vector equation, and this is nothing but this A, and this is equal to 1 by rho del P plus G, and this part is nothing but summation of F by M. Okay, it's nothing, just that. Now let us take a dot product of both sides. Okay, and we want to move along this path, so we are moving from 1 to 2, A dot dl, 1 to 2, summation of all forces by M dot dl. So that's what I did. Okay, so let's open it up. So this would be nothing but del V by del T plus V dot del V dot dl. This is equal to 1 to 2 minus del P by rho plus G dot dl. Okay. Now I need to find, to move forward, I need to find what is this V dot del V. Okay. I need to find what is V dot del V. This is something which I need to find. For that, I know this vector relation del V dot V. This is equal to 2 times V dot del V plus 2 V cross vorticity. This V cross, this omega is nothing but vorticity. If that's the case, then this V dot del V, this would be equal to del V square by 2 minus V cross vorticity, and from there I can get now we know that this vector relation that A cross B is equal to minus B cross A. Using that I can say that del V square by 2, and I can change it to plus sign, and again omega, which is nothing but my vorticity, cross V. So that's what I have with me here. I know it is going a little bit calculus. We are getting a little bit more mathematical here, but bear with me. Bear with me. Bear with me a little bit more, and you would see the fruits of this labor, and you would see really where it is helping. So let me put all of these things up there in my equation, and 1 to 2 del V by del T, this is simple V, del V by del T dot dl plus 1 to 2 omega cross V, again these are vectors, dot dl plus 1 to 2 del V square by 2 dot dl. This is equal to minus 1 to 2 1 by rho del P dot dl plus 1 to 2 G dot dl, okay, G dot dl. Now G, I know already that G is along minus Z direction only. So I know what this G is. It's along that direction only. And then I also know about the relation that for any phi scalar, del phi dot dl would be nothing but d phi. Okay, using that, let us see what modifications I can have. Del v by del t dot dl plus 1 to 2 omega cross v dot dl plus 1 to 2 d v square by 2. So I have changed this, dv square by 2. I have used this here, this relation. This will be equal to minus 1 to 2 d p by rho plus 1 to 2 minus del of gz, because my acceleration is along z direction, dot dl. Okay, now this RHS can be further, right hand side can be further written into dp by rho minus 1 to 2 d of gz. Okay, that's something which I can write. This can be further modified and we would get our final form now, and this final form is actually, you would see the beauty of it. Del v by del t dot dl, it's d and l separate, plus 1 to 2 omega cross v dot dl. Forgive my joining d and l, it's not a word, it's d separate, l separate, plus v2 square minus v1 square upon 2 plus 1 to 2 dp by rho plus g z2 minus z1 equals to 0. Now, although we have gone through some mathematical labor and pain, but look what we got. This is a general equation in its most general form. It's the most general form where we have only assumed inviscid flow, nothing else. It can be compressible, it can be incompressible, it can be steady, it can be unsteady, anything goes here. The only thing is that this is for inviscid flows, okay, those regions where viscous effects can be neglected. Okay, now I know this equation 1 looks nothing like the Bernoulli equation which you know about, but I can move towards the Bernoulli equation which you all know very easily from here. But the whole beauty of doing it in this way is that I have not introduced any other derivation to you. It's simply Newton's second law, force equals to mass time acceleration, and we are just looking at different facets of it. From there we got our momentum equation with certain modification. For inviscid flows we got our Euler equation. Then we looked at Euler equation in a streamline coordinates, and then we moved from our Euler equation, which was a vector equation, to a scalar equation. And this equation which you have in front of you, equation 1, is the most general form for that. Now, further modifications to make it more palatable, to make it more easy on your senses, something which you understand a bit more or you have seen a bit more. So the unresolved integrals can be further modified if one selects the arbitrary curve to be one of the streamlines of the flow. If you remember the material line which I had shown above, I just said that this is a path which a particle is following. Okay, it could have been a streamline, it could have been other than a streamline, but now we are saying that, let us say that that path which the particle followed was a streamline. Okay, so that particle was moving along a streamline. If that's the case, then we can say that along a streamline we take our coordinate as ds, which would be same as the dl which we have taken. Again, mind by joining d and l. It's a habit problem, but please be sure about it. D and L are separate. No need to join them. If we take that as the case, then let us see what modifications can come. Now, what do you know about a streamline? Just for a moment, I would like you to think about it, and then you would see how we would use it. So del v by del t dot ds plus 1 to 2 and integral, and it's omega, which is my vorticity, cross v dot ds plus v2 square minus v1 square by 2 plus 1 to 2 dp by rho plus g z2 minus z1. This is equal to 0. Okay, now I want to talk about this term del cross omega cross v term. This would go to 0 if we are talking about a streamline. Why? We know that A cross B, if let's say it is A cross B which is equal to C, then we know that C vector is in a plane which is perpendicular to A vector and B vector. We know about it. So it means that here omega cross V is something which is perpendicular to V. Okay. Now, we know that if we are moving along a streamline, then a streamline is made by taking tangent velocity vectors, joining tangent velocity vectors, tangents to the velocity vectors, we get our streamline. So I can say that omega cross V would be perpendicular to ds also. If that's the case, then omega cross V dot ds would be 0, and that's why I have written here. Now V2 square minus V1 square by 2, this is nothing but change in my kinetic energy along a streamline. See, you can come, if you want to derive your Bernoulli equation, you can move to it from the energy side, or you can move to it from momentum equation side. It is one and the same because we are using work energy principle. Okay, it is interchangeable. So now with this modification, if I am moving along a streamline, if I am moving along a streamline, then my equation would be modified to del V by del T dot ds plus dP by rho plus V square by 2 plus Gz, and this is going to be a constant. So this is my second equation, and you can look at it. The first term here, this is an unsteady term. That's why whenever someone asks you that can you apply Bernoulli equation to an unsteady flow, then yes, we can apply Bernoulli equation to an unsteady flow also. The second term gives me here an idea about relationship between pressure and density. So in this particular form, this equation can be applied to compressible flows also. Okay, provided I have a relation between pressure and density, I can apply this equation to compressible flow also. I can apply this equation to unsteady flow also. So this is a general form of my Bernoulli's equation, and generally what you would see in the book or at this stage in other places, that form generally that form is written for steady incompressible flow. So don't confuse yourself with that Bernoulli equation can only be applied to steady and incompressible flow. It's not like that. The reality is that Bernoulli equation can be applied to unsteady and compressible flows also. So up till now, the assumptions which we have taken are that we have inviscid flow, that is the first assumption, and the second assumption is that we are moving along a streamline. These are the two assumptions which we had taken up till now. Now further modifications can be done if density variations are not significant along the streamline. Since everything is moving along a streamline, so it is really important to see that there may be density variations which are significant, but are they significant along the streamline or not? That is important. Okay, along the streamline, and this is not always same as saying that it is an incompressible flow. So mathematically what we are trying to say is that if this thing del rho cross V, it is equal to 0. So if density variations are not significant, then we can write the above equation to as del V by del T dot ds. This integral would go, and we have simply P by rho plus V square by 2 plus Gz. This is a constant, meaning by you can put this equation between any 2 points along a streamline. Furthermore, if the flow is steady, then the first term would vanish, and we would have P by rho plus V square by 2 plus Gz is a constant. Okay. So that's what we have with us simply. Now, if to start with from equation 1, the equation 1 which we had to start with, if we would have said that we have irrotational flow, okay, if we have said that we have irrotational flow, then let us see what would happen to our Bernoulli's equation. If we would have said that we have an irrotational flow, so we know that for irrotational flow, vorticity would be 0. For an irrotational flow, my vorticity vector is 0. Okay, so my equation 1 from very start would have then reduced to simply del V by del T dot dl plus dP by rho plus V square by 2 plus Gz equals to a constant. Now this equation here, I have not assumed that I am moving along a streamline. Please see, I have not assumed here that I am moving along a streamline. So this holds everywhere in the flow field. So there is a bit of difference in this equation. Let me call it equation 5, the way I reached to equation 5 and the way I reached to equation 2. In equation 2, since I am moving along a streamline, so I have taken my dl equals to ds here. I am moving along a streamline. In my equation 5, I am not moving along a streamline. The only thing I have taken is that it's an irrotational flow, but still the form is very much same. So if you understand this complete concept, then although we have done a bit more of a mathematical treatment, but it would make our life much more easier, and this is much more uniform. You don't need to memorize lots of equations without knowing where they are coming from. Up till now, it is like a very beautiful single thread which we are following. Okay, we are moving along a single path only. So it makes, according to me, a bit more easier. But again, you are very much free. Whichever way is easier for you, you can look from book also. And after that, I would like you from any of your books, from Frank and White or from Fox McDonald, look into different applications of Bernoulli's equation. Please look into it, applications of Bernoulli equation. So please see applications of Bernoulli equation and try to do solved and a few unsolved problems from your books, and you can very easily do that. Where this Bernoulli equation is used, there are many places where Bernoulli equation is used, and using this actually we have you can steady flow through orifice, and even orifice meters, venturi meters are designed using this principle. You can also study free jets, what's happening over there, and there are many applications for Bernoulli equation. So I would highly recommend you to look into that, look into the solved problems in this field, in this area from both the books, and then try to do some unsolved problems. There's a possibility that in future I may give an assignment related to that, or if not assignment, then practice problems related to it. So that pretty much finishes our this complete unit on fluid dynamics. and after that we would move on to the final unit, and that's the unit on pipe flow. Up till now, whatever we have studied in our unit 1, unit 2, unit 3, we would try to apply it to a particular problem, and that problem is the problem of pipe flow, to this particular case of pipe flow. So that would be our next.